welcome to the third video in the lecture series on linear algebra. In this video we will go over the topic matrix algebra. So we first define some operations on matrices, and to start with this we denote by this thing here, so A in brackets and then ij, the entry in the ith row and the jth column of the matrix A. So if, for example, we have this matrix, we have that, let me say this is A, say that A, 1, 1, so it will be the entry in the first row in the first column, so this 1 here, so this is equal to 1. Right, so with that in mind, we define the following things. So we let A and B be n by n matrices. Then we say that A and B are equal if they all have the same entries. So for every I and j, we have that this thing is equal to this thing. Then we define the scalar product. So for some scalar C and F, we say that the matrix CA is the matrix defined by C times Aij. So we take the entry of the matrix and multiply it by C. Then the sum of A and B is defined as the matrix where we sum all of the entries of A and B, but we need to keep in mind here that A and B have the same size, so we cannot add matrices that don't have the same dimension, nor can we say that they are equal. Yeah, so with this we can start to define more interesting things on matrices. So we first want to motivate why we want to define these operations, and the first operation we will define is, or want to define, is matrix multiplication. So we want to write our linear system in a compact way, where we have we have our matrix A, our vector B, and the vector of unknowns x. And to write this in a compact way, we will discover a nice definition for the product of two matrices. So to do this, we first need to define the scalar product of two vectors. You might have already seen this in some of the other presentations of the other lectures, but I will go over it again here. So we have A and B, which are n vectors, and we denote the transpose of A as a to the power t, which I'll just call A transpose, which is just basically rotating this column here by 90 degrees to get a row vector. Then the scalar product of A and B is basically A transpose times B, where we multiply this A1 by B1, A2 by B2, etc., etc. And so we get this sum from k equals 1 up to n of AK BK. Then, with this in mind, we can define a matrix multiplication. So yes, we continue by defining matrix multiplication. So let A in F n by n and B in F n by k. Then the matrix product AB in F n by k is the matrix defined by this mess here. So basically what we do is we take the ith row of A and the jth column of B, and we take their scalar product, and we say that is the ijth entry of AB. So I think it is better to see an example of this, because this is quite a hefty definition, and you might want to pause the video here and read over it again. So yes, this might cause some question marks. And a very important thing to note is that from this definition, we see that the matrix product is only defined for matrices where the number of columns of A equals the number of rows of B. So in this case, A has n columns and B has n rows, so we can take their product. Right, so let's do an example. First we do an example of the scalar product. So we have A is this column vector and B is this column vector. And then their scalar product, we multiply this 1 by this 4, this 2 by this 5, and this 3 by this 6, and we add them. So we can imagine this as pairing these numbers up with the same color. And then we multiply and we add, and we find that this is 32. Right, so let's now do an example of a matrix multiplication. So we let A be the matrix with A and B as its columns, and B be the matrix with A and B as its rows, by taking transposes. Then, taking their product AB, we first, what we do basically is we think about going row into column. So what I mean by that is we look at the first row of A, so this 1, 4, and we multiply, like basically we take the scalar product with that, the first column of B, so this 1, 4, so that will be 1 times 1 plus 4 times 4. And we do that for every row and every column. So first we take, first we take 1, 4, 1, 4, then 1, 4, 2, 5, 1, 4, 3, 6. Then we do the same like this, etc., until we have covered everything and we get a 3 by 3 matrix. So if you go through this process, I will not do the details here, you can pause and look and check for yourself that this is indeed correct. You will find that this matrix. So we can see that multiplying matrices can also change the matrix product AB can have different dimensions than either A or B. And there's a nice method of doing this, which is called Falk scheme. So if you find it, this row into column method, you don't really, you find it difficult to remember, you can try Falk scheme. So what you do is you put the two matrices like this in order of their multiplication, because matrix multiplication is not commutative, as we will see later. So AB is not necessarily the same as BA. Then you put two lines like this. Remove this guy. Oh, okay, never mind. And then you simply go like this. So this 1 pairs up with this 1, this 4 pairs up with this 4, and then you multiply these and add them to the product of these two. You do the same like this, and the same like this, etc., and then you will also find this answer. You will find the 3 by 3 matrix. I hope that was clear. If you have any questions, again, you can always email me. So now we return to the aim that we initially had, which was to rewrite our linear system in a compact way. So we see that this complicated system, which we sort of try to get away from by writing this LEAB, we can rewrite it as AX equals B, because if we have, okay, so I can just explain. If you work out the product of A and X, you will find these equations that you see here. And of course, B is just on this side, so we don't see anything with B. And this is a very neat way of writing a linear system. Okay, with that, we can get on to some properties of matrices. Now that we've defined matrix addition, scalar multiplication, and multiplication. So we have a theorem summarizing these properties. So the following hold for all scalars alpha and beta and matrices ABC, provided that the given operations are well defined. So we have that A and B have the same dimensions when they're added, etc. So matrix addition is symmetric, so, or not symmetric, commutative. A plus B is the same as B plus A. This makes sense intuitively because normal addition is also commutative. So if we add all the entries of the matrices, it should also be commutative. Then we have commutativity when we add three matrices, basically. So we have A plus B plus C is the same as A plus B plus C. Then we have that the order of matrix multiplication does not matter. So multiplying AB first is the same as multiplying BC first and then multiplying by A. Then we have distributivity. So A times B plus C is the same as AB plus AC. Again, different type of distributivity. So this is left distributivity and this is right distributivity. As I told you before, matrix multiplication is not necessarily commutative, so we need to state this. And then we have that multiplying our two scalars first, and then multiplying A by them, or multiplying A by beta and then by alpha is the same. So yeah, scalar multiplication of matrices does commute. Yeah, so again, very important in general, matrix multiplication is not commutative, and we will now see an example of this. So in a previous example, we had these matrices A and B, and we had their product AB. But if we work out the product BA, we see that this is a 2 by 2 matrix, and so AB and BA do not even have the same dimensions. And so we need to be very careful that matrices do not behave like scalars when you multiply them. Okay, now we define another operation on matrices, which is the transpose. So the transpose of a matrix is this matrix, which we call A transpose, which is basically just defined by, so if an entry of a matrix is on position 2, 1, we put it on position 1, 2. It is easy to see how this works with an example. So for example, in this matrix, we take the transpose, and this 2 here is in column 2, row 1, so in position 1, 2, so you remove it to position 2, 1, which is in row 2, column 1. And we do this for every entry, and the way you can memorize this is to see that this diagonal, so this here is fixed. So basically you reflect all the entries along this diagonal, and in that way you have the transpose of the matrix. Now we have some more properties of the transpose. So again, we have for all scalars alpha, matrix AB, blah blah blah. These operations are provided they are defined. This holds. So the transpose of the transpose is just the matrix itself. This makes sense because if you reflect twice, you will get the same matrix back. Then multiplying by a scalar and then taking the transpose is the same as multiplying the transpose by a scalar. This also intuitively makes sense. If you take the matrix and multiply all the entries by a scalar, and then take the transpose, it will be the same as transposing and then taking multiplication by a scalar. The transpose of the sum is the same as the sum of the transposes. Yeah, okay, this should also make sense, I hope. And then we have this law, which is a bit more difficult to prove. I will not include the proof here, but it is important to memorize as it comes up sometimes in matrix algebra. So we have that if you have a matrix product AB and take their transpose, that is the same as B transpose times A transpose. Okay, with that, I would like to end this video on matrix algebra, and I will see you in the next video where we discuss non-singularity.